A new vest design could cut cancer risk for astronauts heading beyond Earth's protective field. This is Fascinating Frontiers, episode 173. The vest uses layered materials to block high-energy particles that penetrate spacecraft walls during long missions. Researchers tested prototypes showing measurable dose reduction for crews traveling to Mars or beyond the magnetosphere. The design targets galactic cosmic rays that current hull shielding leaves unaddressed. Follow-up trials will measure performance in simulated deep space radiation environments before any flight hardware decisions. Engineers focused on materials that remain lightweight while providing consistent protection across different particle energies. The vest is intended as a wearable supplement rather than a replacement for spacecraft shielding. Data from the prototype tests indicate lower absorbed doses in key body areas during exposure periods. Now shifting to conditions on Earth itself. Landsat satellite images spanning decades reveal how breeding colonies shift when fast ice breaks up earlier each season. Scientists track colony locations and sizes to map which sites remain stable and which are abandoned. The data helps separate natural variability from longer-term ice loss trends around Antarctica. Continued monitoring will show whether colonies can relocate fast enough to match the changing coastline. Images captured over multiple decades allow comparison of colony positions relative to the ice edge at consistent times of year. Researchers examine both the timing of ice breakup and the distance colonies must travel to reach stable breeding platforms. The analysis distinguishes short-term fluctuations from sustained changes in ice duration. On a different note, new models are revealing how entire galaxies keep their centers in balance over billions of years. A team at the Leibniz Institute for Astrophysics Potsdam ran high-resolution galaxy models that couple central black holes with their surrounding stellar disks. The runs show gas inflows and stellar feedback keep the central regions growing in step over billions of years. The models reproduce observed Milky Way properties such as the boxy bulge and nuclear star cluster. Next steps include comparing the simulated stellar populations with upcoming spectroscopic surveys. The simulations incorporate both gravitational dynamics and gas cooling processes at high spatial resolution. Results indicate that feedback from the central black hole regulates the rate of new star formation in the inner galaxy. The modeled stellar orbits match the observed boxy shape of the Milky Way bulge. Understanding how galaxies grow pairs naturally with the infrastructure that lets us study them from afar. The new dish at the Goldstone complex adds capacity to the 34-meter subnet used for tracking missions across the solar system. It joins 3 existing antennas and will support more than 40 active spacecraft once commissioned. Engineers completed integration and began initial pointing tests this month. The addition helps maintain continuous coverage as multiple Mars and outer planet missions operate simultaneously. The antenna increases the network's ability to receive weak signals from distant probes without extending existing observation schedules. Commissioning activities include calibration of the radio frequency systems and verification of tracking accuracy. Once operational, the new dish will share the load during periods when several spacecraft require simultaneous contact. More listening power on the ground comes at a time when we are learning how quickly planet-forming material can disappear. Observations of several young stars reveal that the gas reservoir needed for giant planet growth disperses on timescales shorter than previously modeled. The telescope measured ultraviolet and infrared signatures of photoevaporation driven by the central star's radiation. This process appears stronger in disks around higher mass stars, altering the window available for planet assembly. Follow-up programs will target additional disks to test how stellar type and disk mass affect the dispersal rate. The measurements capture the rate at which gas is lifted away from the disk surface by stellar ultraviolet light. Disks around more massive stars show faster gas loss, narrowing the time available for cores to accrete thick atmospheres. The findings adjust earlier estimates of how long the gas phase lasts in typical planet-forming environments. JWST observations of dispersing planet-forming disks show that the gas giant formation window can close in just a few million years. The telescope captured direct tracers of ultraviolet-driven winds leaving the disk surface, confirming that stellar radiation, not just internal turbulence, removes the raw material. This tightens the timeline models must satisfy and raises the question of how often massive planets still manage to form. What fraction of disks lose their gas before cores can accrete thick envelopes? Picture a disk of gas and dust around a young star the size of our entire solar system. Now shrink that disk until its outer edge sits inside the orbit of Jupiter, and you have the typical scale where gas giants must finish forming. Inside that compact region, the central star's ultraviolet light heats the disk surface to thousands of degrees, launching a wind that carries away hundreds of Earth masses of material each million years. The process is fastest near the star, so the inner disk empties first while the outer regions linger, creating a shrinking reservoir that planets must tap before it vanishes. One surprising measurement from recent observations shows some disks lose half their gas in under 3 million years, a timescale shorter than the orbital period of Neptune around our own sun. Yet we still do not know why a few disks retain gas far longer than their neighbors, even when the stars appear nearly identical. The unanswered question is whether an unseen companion or a different magnetic field geometry can suppress the wind and buy extra time for planet growth. Models must now account for the possibility that only a narrow subset of disks survive long enough for giant planets to assemble their envelopes. Observations continue to reveal that the dispersal mechanism operates across a range of stellar masses, yet the exact efficiency remains difficult to predict from star properties alone. Future datasets will test whether external factors such as nearby massive stars can accelerate or slow the loss of gas in otherwise similar systems. With planet formation timelines tightening, it is worth noting how future explorers might one day recycle what they already have on the Moon. The agency will name the final phase winners of its LunaRecycle Challenge on August 28th at the University of Alabama. The competition asked teams to design systems that turn non-metabolic waste into usable resources for future lunar bases. Finalists have been testing prototypes that process plastics, metals, and other station trash. The results will inform technology roadmaps for sustained surface operations. The event will take place at the University of Alabama's Lee Styslinger College of Engineering in Tuscaloosa. Teams developed hardware capable of handling waste streams that do not include crew metabolic output. Prototype evaluations focused on conversion efficiency and reliability under simulated lunar conditions. While hardware challenges continue, a new academic program is preparing the next generation to tackle them. Several colleges are combining courses in engineering, planetary science, and policy into a single minor available starting next academic year. Students will complete a capstone project that can involve mission design, data analysis, or science communication. Faculty from multiple departments develop the curriculum to prepare graduates for roles at NASA, commercial space firms, and research institutes. Enrollment opens this fall for the 2026 to 2027 catalog. The program draws on existing courses across engineering, science, and social science departments to create an integrated pathway. Capstone options allow students to choose between hardware design projects, analysis of mission data sets, or public outreach activities. The curriculum was shaped by faculty input to align with workforce needs at government agencies and private companies. Registration for the first cohort begins during the upcoming fall enrollment period. Before we go, keep an eye on follow-up JWST targets that will test how stellar type and disk mass affect gas dispersal rates. That covers today's space and science news. Share this with a fellow space enthusiast if you found it interesting. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at NERA Network. Links in the show notes. And before you go, this show is part of the NERA Network, a family of daily podcasts on tech, science, and markets, each one a short, sharp briefing you can finish on the commute. If today earned its place in your feed, here's your next listen. SpaceX Daily, the daily companion for following SpaceX as a public company, from Starship to the stock ticker. Find every show free at neranetwork.com. And on the website, every episode's visuals live in our free image gallery at neranetwork.com gallery. Royalty-free under Creative Commons, download with attribution. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.
drifting softly through